All right, welcome ladies and gentlemen. This is video number 1 for liquids and solutions. You're going to need your note packet open up to page 8. And this first video we're going to be going over the dissolving process, dissociation of ionic compounds, what that means, what that looks like, and a phrase called like dissolves like. So first up we have a whole bunch of definitions. Solution, when we say solution in chemistry, we are referring to a homogeneous mixture. So just a reminder that homogeneous means same. It looks the same throughout. So it's a very evenly mixed mixture that has something dissolved in something else. So if you think of sugar in water, that is a homogeneous mixture, that is a solution. And an aqueous solution is really the one that we're going to be focusing mostly on, because an aqueous solution is one where water is the substance that contains the dissolved particles. So dissolving sugar in water would be an aqueous solution. The solvent is the substance that does the dissolving. In an aqueous solution, that would be water, right? Water is your solvent in an aqueous solution. And typically speaking, your solvent is your thing that you have more of. If you think of dissolving salt in water, you have way more water than you do salt. Water is the solvent. Versus solute, the solute is the substance that is being dissolved. And it's typically present in smaller amounts. Solubility. We will be using this term a lot in this unit. Solubility simply refers to how much of something was dissolved in something else. And when we say how much, we're going to be talking here in number of grams. We might also be talking about number of moles that are dissolved. So when we say how much, we really are referring to a specific amount, a specific number of some sort of unit, measuring how much of a solute gets dissolved into a solvent. And then we're going to be using the words soluble and insoluble a lot. So soluble means that something does dissolve. It can dissolve. So, sugar is soluble in water. Sugar dissolves in water. So what does that look like if something is soluble? If something's soluble, the mixture that you get at the end, that homogeneous mixture, it's going to look like a liquid. It's essentially going to look basically about the same as it did before. If you think of sugar water, it basically looks just like water. You can see through it, right? It's transparent. And that's a big thing. Versus insoluble, which means that something doesn't dissolve. Things that don't dissolve in water, like rubber is insoluble in water. It will not dissolve in water. And if you're trying to dissolve an insoluble thing in water, you're going to see a clear separation between the water and the insoluble compound. It will be very apparent that they are not dissolving in one another. And most of the time for us, that's going to mean that we're going to see a solid at the bottom, and we're going to see water usually on the top. It doesn't have to be that way, but we're going to obviously see this difference. We're going to see this solid. And if it is a solid, if we are getting a solid, then it might look a little opaque. It won't be transparent. So a typical question about this sort of thing, which of the following is a homogeneous mixture? This could very easily be a Regents question. And we have these 4 options. If we're looking for the thing that's the homogeneous mixture, we want to look for the thing that obviously has 2 components, because that's what makes it a mixture, right? A mixture is 2 separate things. And the homogeneous bit means that it's going to be an evenly mixed mixture. Now, when we look at these options that we have, there's only one important part of each option, and it's actually not the compound. The compound out in front is completely irrelevant. What's important is the phase of matter that's listed next to it. A liquid and a solid, these only have one component. In this first option, NH3 liquid, you only have NH3. You don't have anything else. It cannot be a mixture. Likewise with solid water. With solid water, the only thing we have is water, and that's it. That's not a mixture. But this sucker right there, when it says aqueous, aqueous means that you have the compound that came before it, meaning you have the sodium chloride, but then you would also have water. You would have 2 things present. So the aqueous sodium chloride, that is, oops, sorry, let me go back. That is the homogeneous mixture. It's an aqueous solution. That's what makes it the homogeneous mixture. Sorry. So dissolving versus dissociating, or the dissolving process. A really, really important point about ionic compounds, and this is specific to ionic compounds. Molecular compounds with things that have covalent bonding, they don't do this. But if you put an ionic compound in water, if it's soluble, then the ionic compound will break up into its specific ions when it's dissolved. And we call that process dissociating. So sugar dissolves in water, but it actually doesn't dissociate in water because sugar doesn't have any ions. But sodium chloride, salt, when you put it into water, it both dissolves, meaning it forms the solution, and it dissociates, it splits into its separate ions. So this is the massive point. And this is true for all ionic compounds that can dissolve in water. When you put them in water, sodium chloride, it's not NaCl anymore. It's not together. The ions won't be bonded to one another anymore. It splits apart and it becomes the separated ions, and these ions become totally separated from one another. So what we have here is a picture showing this idea. You put an ionic compound in water, and this is NaCl, and on the left, we have NaCl solid. So this is just table salt like it would be sitting out on your table at home. And then you put that into water. And this is like putting it into water right away. And you see it's starting to dissolve. It's starting to split up. But then this is the final over here. And notice that the ions are separated. We call that dissociation. The ions have completely split. The sodium ions are separated from the chloride ions. And again, all ionic compounds will do this. They will split into their ions when you put them in water. Looking at this a little bit more, what happens in this process, the reason that this happens is because water is a polar molecule. So it has the partial negative and the partial positive ends. It has the two separate ends. When you put the ionic compound in water, well, the ionic compound has charges. The green is the chloride, that's the negative charge, and the blue is the sodium, that's the positive charge. So the water molecules surround the ions because opposite charges attract. Your oxygen is your slight negative end, your hydrogen is your slight positive end. Notice the sodium, which is positive, has all the oxygens, all the partial negatives of the oxygens are surrounding it, and it's causing, the water is essentially pulling the positive ion away from the other negative ions. And likewise, when we have the chloride ion, which is a negative charge, notice all the partial positives of the hydrogens in the water are now surrounding it. So this helps in this dissociation. The water essentially prevents the ions from getting back together. Like dissolves like, this phrase like dissolves like. Well, not all compounds are soluble with one another, and this phrase like dissolves like essentially is explaining why. What compounds can mix with one another? For example, oil and water. That's what's in this picture right here. Notice we have the oil layer and the water layer, and they are completely separate. They do not dissolve one another. We have this very clear separation between the oil layer and the water layer. Well, why is that? Everything lies in this right here. Oil is a nonpolar compound. It's symmetrical. It has even distribution of charge, right? Remember SNAP, symmetrical nonpolar, asymmetrical polar. Water, on the other hand, is a very, very polar molecule, extraordinarily polar. Water is one of the most polar things that's out there. And it comes down, and this phrase, like dissolves like, has to do with polarity. It means that polar compounds can dissolve other polar compounds, but they can't dissolve nonpolar things. Polar dissolves polar, i.e. like dissolves like, and then nonpolar can dissolve nonpolar compounds, i.e. like dissolves like, but if they do not have the same polarity, they're not going to dissolve in one another. So polar molecules dissolve polar molecules, and nonpolar molecules can dissolve nonpolar molecules. The reason is actually all about intermolecular forces of attraction, IMFs, that idea of how well different compounds stick to one another. You might remember we talked about different molecules having different types of intermolecular forces of attraction. Hydrogen bonding is the strongest type of IMF, and you can only find it in polar molecules, specifically polar molecules that have an H that's bonded to an NO or F, so that H-NOF, right? H-NOF are the elements involved in hydrogen bonding. And when you have things with the similar polarity, polar molecules and polar molecules, they're going to form the same types of intermolecular forces of attraction with one another, and that's what gets them to dissolve. Nonpolar molecules have their own type of IMF, right? London dispersion forces, which everything has, but that's their only type of IMF. So when they dissolve, because they have the same type of IMF, they can actually dissolve in one another. Same polarities. And the absolute huge key point here, if two substances have similar polarities, that's the like dissolves like, they will dissolve in one another. If they do not have similar polarities, they will not dissolve in one another. And just looking at a picture of this a little bit more, this is ethanol in water. So this first picture says when we mix the ethanol in the water, we get an initial separation. Just because when you initially add them together, you're always going to kind of get this initial separation. We have hydrogen bonding. Remember, that's H-NOF, and that's a super strong IMF. And we have hydrogen bonds between ethanol molecules, and we have hydrogen bonds between water molecules. So they have the same type of IMF. And because they have the same type of IMF now we can make that IMF in between the two separate types of molecules. Like dissolves like. They have the same polarity. They're going to have the same types of intermolecular forces of attraction. So these two things can mix with one another. They can form hydrogen bonds with one another. Like dissolves like. So that's the end of the first video, and we will be playing around with some like dissolves like demos in class.